So hello everyone, I'm Haruka Kiyohara and I'm an undergraduate student from Tokyo Institute of Technology. And today I'm very excited to share our work leveraging context-dependent click model for policy variation of ranking policies. So ranking decision making is everywhere in web services, from search engine to music streaming service, e-commerce platform, and newsfeed. In those applications, it is very important to present relevant items to the user to increase sales or user satisfaction. So today, I'm gonna talk about how we can evaluate the value of this ranking recommendation using only offline log data. To start, ranking recommendation is often described as a contextual bounded process. So when a user first comes to the system, we present some ranked list of items to the user, which consists of total K items inside. And then we're gonna also observe some user feedback, such as click as reward for each position in the ranking. And now, what is important in this process is that we are often having an underlying algorithm that chooses which item to present to the user. So it's very important to evaluate if this ranking policy pie successfully produces, a very relevant ranking to the user, or if this ranking policy failed to do so. So as the performance measure of this ranking policy pie, we are now interested in its policy value, which is defined as the expected aggregated reward obtained by deploying this ranking policy pie. And this ranking-wise policy value is often decomposed into the position-wise policy value. So today, I'm gonna talk about how we can evaluate or estimate this position-wise policy value of the given ranking policy pie. And now, going back to the previous slide, let's consider the case where we are having a logging policy in the system. So this logging policy interacts with users. Sorry. Oh. Okay, it's working. So this login policy interacts with users on daily basis. And at the same time, this login policy also collects variable log dataset. Oops. Okay, a variable log dataset containing the past interaction in the system. So here, our goal in policy variation is to utilize this variable log data to evaluate a new evaluation policy in the system. So this policy variation is a statistical estimation problem of the position-wise policy value of the given evaluation policy pie using the log data collected by the different logging policy pie now. And of course, this policy variation is quite beneficial in practical situation because we can now enable safe offline A/B test to evaluate this evaluation policy. But the problem here is that we are often having the distribution shift between the login and evaluation policy. So the de facto approach of policy variation, called inverse propensity scoring, applies important sampling technique to correct the distribution shift between the login and evaluation policy. And in this way, this IPS enables unbiased estimation, which is very nice. However, this estimator is also known to suffer from a high variance when the importance weight is very large or there's weak overlap between the login and evaluation policy. And especially in our ranking setting, this variance problem can be problematic because when we calculate the number of total possible combination of actions, it can grow exponentially as the length of ranking grows. So maybe the number is a bit small, but it's over 1 million, right? So it's huge action space, right? So this risk, makes the importance weight very large because we have weaker overlap between the login and evaluation policy as the length of ranking grows. So we need to deal with this very huge action space and also the resulting variance problem. So the existing approach in ranking recommendation often assumes some user behavior assumption to make this combinatorial large action space to a tractable one. So for example, in this independent IPS, we assume that the reward observed at each position depends only on the corresponding action. And by assuming so, we can now reduce the combinatorial large action space to a single action space, so we can greatly reduce the variance of the original IPS. However, of course, there's pros and cons in this approach, and since we are now having a very strong assumption, when this assumption does not hold and the reward is also affected by some neighboring items or previously observed items, this estimator, independent IPS, incurs serious bias in estimation. And another popular assumption is called cascade assumption, which assumes that user browses the item sequentially from the top. And by assuming so, now the reward observed at each position depends only on the higher position. So we can again reduce the variance of the original IPS while remaining less biased compared to the very strong independent IPS. However, when this assumption does not hold, this RIPS still introduce high bias in estimation, and also this RIPS suffer from a high variance when the ranking size is very large. So now, summarizing those existing estimators, we see here that there's a clear bias variance trade-off depending on the user behavior assumption we assume. And also, we now realize that these estimators all assume a single universal assumption to the entire population of users. For example, RIPS assumes that everyone follows the cascade assumption, right? But in reality, in the real-world situation, we know that user behavior can be very heterogeneous and can change heavily depend on the context. So for example, in neural critic modeling literature, we often assume that user behavior can change depending on the user context, such as search query or user's browsing history. So our question here is that why not using adaptive user behavior to capture more diverse user behavior to enable more effective bias variance trade-off in policy evaluation? So let me give you the intuitive understanding of our approach. So we are now having this kind of situation, and we now have very heterogeneous users in the system, and they have very different search queries or browsing histories or other user context. And depending on this user context, these users also have very diverse user behavior, such as cascade or independent or more complex user behavior. And the biggest limitation of all existing estimators is that they are now assuming a single universal assumption to the entire population of users. So it often produces significant mismatch between the true user behavior and the estimator's user behavior assumption. So our idea here is very straight. So let's just use, adaptive user behavior so we can reduce the mismatch between the user behavior assumption and the true user behavior. And the mismatch, leads to, serious bias or excessive variance. So we can now enable more effective policy evaluation, right? And based on this idea, we're gonna now define our GIPS estimator, generalized IPS, the adaptively switches the importance weight. So what we are assuming is that now the reward observed at each position depends only on the relevant action specified by this true user behavior model index C. And by applying importance sampling only for relevant actions, we can now use minimum sufficient user behavior assumption. So we can now enable unbiased estimation under given true user behavior model, while also achieving the minimum variance among all IPS-based unbiased estimator. And looking at the variance reduction effect, we now find that GIPS reduces the variance of irrelevant actions because we are now applying importance sampling only for relevant actions. And since relevant action depends on the user context, by using context-dependent importance weight, we can now achieve a very good statistical properties. Right, so let's finally look at the experimental result. And here we conduct a synthetic experiment using this reward function, which is affected by the interaction from relevant action. And this user behavior index C determines which actions are relevant to the given position. And since this is a synthetic experiment, we simulated various user behavior distribution, and we changed the user behavior index C from a simple one to the complex user behavior, and also to the diverse user behavior that heavily depends on the user context. And seeing the result, we compare the mean scale error of estimation. So the lower value means that the estimator is more accurate. And seeing this result, we now find that our GIPS estimator, this green line, enables very accurate policy variation across range of user behavior distribution. Because, yeah, as we show theoretically, our GIPS reduces the variance of IPS while also remaining unbiased, even under diverse or complex user behavior. So we can enable very accurate policy variation in more realistic, complex user behavior. Right, so let me wrap up this presentation now. And today, I talked about policy variation of ranking policies, which suffer from a severe bias variance trade-off due to the combinatorial large action space. So to tackle this combinatorial large action space, existing estimator assumes some user behavior assumption. However, it was the single universal assumption to the entire population of user. It leads to the mismatch between true user behavior and the estimator's assumption, leading to either serious bias or excessive variance in estimation. So to deal with this issue, we proposed our GIPS estimator, which adaptively switches the importance weight depending on the context-dependent user behavior. And we show that GIPS enables very accurate policy variation even under diverse and complex user behavior, which is in more realistic situation. And we also plan to further study the robustness of our GIPS estimator to the estimation error of user behavior assumption. Yeah, because true user behavior is often unobservable in real world situation. And I'm very excited to further study, further make this GIPS estimator and work in even more practical situation. Okay, so thank you for listening.